Question 3. Figure 1 represents the cell used to measure the standard electrode potential for the Fe3 plus Fe2 plus electrode, which is this beaker on the right hand side. Name the piece of apparatus labelled A. A is a salt bridge with something like potassium chloride in that's going to allow the ions to move between the compartments and complete the circuit. State the purpose of A. It's going to allow the ions to move or flow to complete the circuit. Name the substance used as electrode B, so you want something that's inert like platinum. Identify C, D and E and the conditions for each. So C is some acid like hydrochloric acid, and it's got to be at 1 mole per decimeter cubed. D is hydrogen gas, and it's got to be at 100 kilopascals and 298 Kelvin. So 100 kilopascals is normal room pressure and 298 Kelvin is 25 degrees C or normal room temperature. And E is the solution of Fe3 plus and Fe2 plus, and that's got to be at 1 mole per decimeter cubed as well. Now you could name something. You could put Fe3 plus and Fe2 plus ions, and that will get you the mark, or you could name it something like FeCl2, which is Fe iron 2 chloride, and FeCl3 iron 3 chloride. You could name other soluble iron salts as well, or you could just put Fe2 plus and Fe3 plus if you wished. The standard electrode potential for this electrode is 0.77. Give the ionic equation for the overall reaction in the cell. State the change that needs to be made in the apparatus to allow the cell to go to completion. Well, the hydrogen gas, H2, is going to go to H+, and at the same time, your Fe3 plus will go to Fe2 plus. So hydrogen goes to H+, and Fe3 plus goes to 2 plus. You know Fe3 plus goes to 2 plus because this here is oxidized, so the other one must be reduced. So 0 oxidation state to +1, the hydrogen has been oxidized, so it's going to act as a reducing agent and reduce the Fe3 plus down to Fe2 plus. How can you make sure the reaction goes to completion? You remove the voltmeter. Removing the voltmeter allows the reaction to go to completion. Now you've got to plot these points on the graph, and it will look like this. So you've got to work out natural log of concentration of zinc 2 plus and copper 2 plus in this cell now. So a different cell. You've got to work out the missing value here. So if I do Zn2 plus concentration 1 divided by 0.1, and then I natural log it, it will come out as 2.3, so that's 2.3 in there. And then it says plot a graph of these values here, 1.16 down to 1.04. So if it says plot a graph of something, the first thing that it mentions is on the y-axis. So 1.16 down to 1.04. You don't need to go down to 0. If you go down to 0, then it's not going to fill up half the page and you're going to lose a mark. And the other values here go from minus 4.61 to plus 4.61. So you might as well go minus 5 to plus 5. That's what I've done there. Suitable scales, points plotted, line of best fit, and using at least half of the page will get you all of those marks. I've got a complicated equation here that's been given to you. The electrode potential of the cell equals minus 4.3 times 10 to the minus 5 multiplied by T, where T is temperature, multiplied by natural log of concentration of Zn2 plus divided by concentration of copper 2 plus a constant, the standard electrode potential. Anyway, you've not really got to use this that much. You've just got to work out that it equals Y equals mx plus C. So my Y value equals mx plus C. So my Y value is this one. This part in brackets must be m. M is the gradient of the graph. When x, this part is x plus a constant. So what it's basically telling you is that minus 4.3 times 10 to the minus 5 multiplied by temperature T is the gradient. So once you work out your gradient is the change in y. So it's going from 1.16 down to 1.04, so that's 0.12. So 0.12 divided by this value here, which is almost 10. So 4.61 plus 4.61, it's 9.22. So it's 0.12 divided by 9.22, and it comes out as a value of minus 0.13. Remember, if your values, if you line of best fit, if you're working out a gradient that's coming down this way, it's a minus value. If it's going up this way, it's a positive value. So if it's going uphill, it's a positive value. If it's going downhill, it's a minus value. So the gradient is minus 0.1013, and the gradient equals all of this value here, minus 4.3 times 10 to the minus 5 multiplied by t. Take this across to the side, so t is minus 0.013 divided by minus 4.3 times 10 to the minus 5, and it'll come out around about 302, 303, and it's in Kelvin. Okay. In experiment 2, the electrode potential of the copper Cu2 plus to copper electrode is plus 0.33. Use the data in the table to calculate electrode potential for the Zn2 plus to Zn electrode in experiment 2. So I've got to look at experiment 2. In experiment 2, the overall electrode potential is 1.13. So I've got to work out what my value of, if the copper 2 plus going to copper is plus 0.33, I've got to work out what Zn 2 plus to Zn is. It must be a negative value, so it's minus. If this is a negative value, it means it's going to go the other way. So I'm going to reverse the sign on this, and it'll become plus 0.8. Plus 0.8 added to plus 0.33 gives me the value in experiment 2, which is 1.13. Okay, give one reason why the calculated value is different from the standard electrode potential using non-standard conditions. For a start, the temperature is not at 298 Kelvin.